cloud and do that. Okay. All right. Operational MOSFETs. This is what we have been talking about, MOSFETs. Questions, please. Questions so far about MOSFETs. What questions do you have at this point about MOSFETs? Okay, so what we did was to look at the regions of operation for MOSFET. We looked at the large signal operation of a MOSFET. Okay, just give me a second while my Apple Pencil is going to connect via Bluetooth. Doesn't want to do for some reason now. Okay, let's see if there you go. Perfect. So what we have been doing is to look at the large signal operation of MOSFETs. Okay, and saw that NMOS, when I draw the symbol for NMOS like so, okay, there is the drain, there is the gate, and with the arrow is the source. Okay, and the direction of the or the location of the terminals, drain, gate, and source, that should give you hints about the voltages that you want to see on the drain, gate, and source with respect to the different regions of operation. If drain is greater than gate, okay, this is also called overdrive voltage or on voltage, and a bunch of different names, VDS SAT. Okay, if this guy is greater than or equals to, if the drain voltage is greater than gate, okay, then you know for the fact that it is in saturation. Okay, let's say here is my gate. Let's say that's my gate voltage. Okay, the drain needs to be up here. That's where the drain needs to be. Okay, if the drain is equals to the gate, okay, that's still in saturation. Did we see that in the last class? If the drain is equals to the source voltage, the gate voltage, that's still in saturation. Okay, the drain can fall below the gate voltage by one threshold voltage and still be in saturation. Okay, so in other words, if the threshold voltage of this guy is 1 volt and the gate is at 3 volts, okay, this equation will be satisfied. Okay, this equation will be satisfied for all values of VD is equals to 2 or higher. Okay, for all values of VD equals to 2 volts or high, this equation is going to be satisfied. VD is going to be greater than VGS minus VT, and then the MOSFET is going to be in saturation. Okay, so the idea that this guy has a special significance. Okay, let me highlight that. This voltage is where, okay, if VD equals to VG minus VT, okay, drain is below the gate by one threshold voltage, okay, or VT or VTH. I keep using the VTH and all of these terms interchangeably. Okay, that's called the edge of saturation. Okay, for the drain voltages above this guy, it's going to be in saturation. For the drain voltages below this guy, it's going to be in linear region. Okay, that's the idea of saturation and linear region. Okay, that's the relationship between the drain and the gate voltage. Okay, that determines whether the MOSFET is in linear or in saturation region. Okay, but what determines if the MOSFET is on or off in the first place? That's the source voltage. Okay, the source voltage, the relationship between the gate and source voltage, this determines on or off. Okay, the relationship between the gate and drain voltage, this determines the saturation or linear region. Okay, so for the MOSFET to be on, I want the gate voltage to be higher than the source voltage by at least, so let me relocate this edge of saturation over here. So the source voltage, okay, the source voltage is below the gate by one threshold voltage. Okay, notice that this threshold voltage should be equal to that threshold voltage, but I'm just showing them separately. Okay, both of these should be equal. So this is not to scale as it is for you to understand. Okay, it's not so much to scale as it is for you to um, understand the interrelationship. Okay, so the idea is that the gate voltage should be above the source voltage by at least one threshold voltage. So if this guy is 3, and I know for a fact that the threshold voltage is 1, so the gate voltage should be at least 2, at the most 2 or below. For all voltages of V source below 2 volts, this MOSFET is going to be on. Okay, the difference between gate and source, the gate should be higher than the source by at least one threshold voltage. Okay, questions please, questions so far. Okay, this is the analysis, this is the visual technique that we use to think about whether the MOSFET is on or not, and whether the MOSFET is in linear saturation or not, or in sub-threshold region. Okay. All right. So here is the idea that is discussed. Okay. This guy, the difference between the Vs and V threshold. Okay. That's shown over there. Okay. This guy, Vg minus Vt, that guy is called the overdrive voltage, VGS minus Vt. Okay. So that's the overdrive voltage. If the gate voltage falls below the threshold voltage right here, then the MOSFET is going to be off. Okay, that's something we know. So for the MOSFET to be in saturation, the drain voltage can be anywhere in this range. Okay, the drain voltage, if VD equals to VG minus V threshold, then it's called the edge of saturation. Okay, this is the condition. If the VD falls below this guy, then it is in linear region. If the VD goes above that guy, it's in saturation region. Okay, so that's the idea of regions of operation of MOSFET. Questions? Okay, so let's see if we can look at some problems. Okay, we'll look at some problems. Let's see, let's look at the first problem, example number 5.2. It's the example, and let's see what information is given. Okay, it's given that we are fabricating in a 0.18 micron technology, and the length is given to be 0.18 micron. Okay, the width is given to be, let's say the width is given to be 2 micrometers. Okay, that's another piece of information given. Okay, the process technology has a C oxide of 8.6 femtofarads. Okay, femtofarads per micrometer square. Okay, remember the C oxide? C oxide is oxide capacitance per unit area of the gate. Okay, you can go back and see that that is the definition I gave for C oxide. Okay, now it bears out, this kind of relationship bears out in the units. There is capacitance per unit area. Okay, when you're converting it to meters or centimeters, or when you're using it, you have to be careful to convert this micrometer square to what it really means is 10 to the negative 6 meter whole squared. Okay, so you want to make sure you take into account that 10 to the negative 12. Okay, so this is oxide capacitance per unit area. The mobility is given to be 450 centimeters squared per volt second. So this is the typical units of mobility of electrons. Okay, centimeters squared per volt second. And you want to make sure you are extremely careful with all the units that we use. VTN or VTHN is given to be 0.5 volts. Okay, so this is all the pieces of information. These are all the bits of information given to us. Okay, that's given. All of this is given. Okay, now there are a few problems that we have to solve. We have to find VGS. The first problem is what is VGS and VDS. Okay, that result in operating edge of saturation. So we are looking at bit A. ID is given to be 100 microamperes. Okay, let's not even worry about B at all. Okay, what is VGS and what is VDS when ID is given to be 100 microamperes, and then we are operating on edge of saturation. Okay, what is the idea that what's the value of VGS and VDS? Okay, we'll do that. We'll do problem A first and then come back to worry about problems B and C. Okay, questions so far, please. Okay, so let me copy the information that's given to us. Copy that and paste it over here. Okay, problem number 5.2. Okay, also we are supposed to find out the value of VGS. ID is given, right? ID is given to be 100 microamperes. Okay, one ID is given to be 100 microamperes. VGS is, are we supposed to find out VGS or we find the value of VGS, find the value of VDS for edge of saturation? What does edge of saturation mean? What does it mean when we say we are on the edge of saturation?
Like limits of saturation where it
Correct.
ends.
The limits of saturation, and we just defined that, didn't we? VD, the drain voltage, is VG minus VTH. Okay, I'll write that equation here. Okay, what's the expression for the saturation condition? Saturation condition. The saturation condition is VDS
VDS is greater than
or equals to
VGS plus VTH.
right?
Yes.
So the limiting condition or the edge of saturation is going to be when VDS is exactly equals to VGS minus VTH. That is what it means to be on the edge of saturation. If VDS goes up, it's going to be in saturation. If it goes down by any small amount, it goes into linear region. Okay, this is precariously balanced on the edge of saturation. So that is shown here as well. VD is equals to VG minus V threshold. Okay, that's something that we saw just now, edge of saturation. Okay, by definition, edge of saturation means VDS. And when I say this 3 equals to, it's by necessity or by definition. Okay, so what we are going to do is to apply the value, the expression for ID, drain current, in saturation. Because we are still in saturation, we are on the edge of saturation. Remember, when VDS is greater than or equals to VT, then we are in saturation. Okay, so there are two equations for current in the drain. I'm going to use the other equation, the equation for the drain current in saturation, which is 1/2 mu n C oxide W over L VGS minus VTH, the whole squared. Okay, does this give any information about channel length modulation? Not yet. Okay, so this is the equation I'm going to use. Okay? VDS equals to VGS minus VT. ID is 1/2 mu n C oxide W over L VGS minus VTH. This is the current in saturation region. Okay, now ID is given to be 100. Or what I'm going to do is, we are expected to find VGS from here. Okay, in order to find VGS, I'm going to rearrange this equation. That's going to come out to be 2 times. So I'm going to take all the terms to the other side, 2 times ID by mu n C oxide W over L. That is going to be VGS minus VTH, the whole squared. Okay, I'm simply manipulating the equation over here. Okay, I'm manipulating the equation. So once I account for the square root is going to show up on the other side. Okay, then I'm interested in calculating VGS, so I take VTH to the other side. Okay, this is more or less a very well-known equation. Okay, once we know the value of ID, mu, and C oxide, pay attention to the fact that we have all of these as knowns. ID is given to be 100 microamperes. Mu n is given to be 450 centimeters squared per volt second. C oxide is given to be 8.6 femtofarad per micrometer squared. W over L is given. Width is given, length is given, and V threshold is given. Okay, accounting for the proper units and plugging in the numbers. And by the way, let me see what the textbook does here. The textbook calculates some interim results. Okay, the textbook, by the way, talks about mu and C oxide. That number is calculated by the textbook to be some K prime N mu n C oxide W over L is calculated to be K sub n. Okay, so the textbook calculates these intermediate results so they can be used over and over again. Okay, you don't have to plug these numbers, do these calculations over and over again if you calculate them. But the idea of calculating VGS, okay, is in order to calculate VGS, we use 2ID over mu n C oxide W over L, square root of that, plus VTH. When we plug in the value, okay, when we plug in the values and account for proper equations, proper numbers, this is going to come out to be VGS equals to 0.22 plus V threshold 0.5. So this is going to come out to be 0.72 volts. Okay, so that's the result we were after in the first place. Tile this to Okay, we were one of the solutions that we were looking for, one of the questions that we were trying to answer was VGS 0.72 volts. Okay, once we know VGS, what would be the value for VDS?
Maybe they are equal.
See, VDS is VGS minus VTH.
VDH.
Remember, that's the edge of saturation. That's the idea of edge of saturation, right? So in edge of saturation, on the edge of saturation, we have VDS to be VGF minus VTH, okay, or which is the overdrive voltage, 0.22 volts. And that's exactly what the textbook goes on to find. V overdrive is that, VDS is this guy, VGS is 0.72 volts. Okay, that's the first part of the problem. The first part of the problem is simply using the equation for drain current in saturation region. Okay, we have to realize that the MOSFET is in saturation and use the appropriate current, and then plug in the numbers carefully, appropriately. Okay. All right, so let's see if we can make some progress and see what the next part of the circuit is, next part of the problem is. Let's look at part B. In part B, if we go back to this, okay, we calculated VGS. In part B, okay, if VGS is kept constant, so VGS is going to be 0.72 volts, okay, and find VDS that results in ID of 50 microamperes. So VDS, what's the value of VDS that results in ID equals to 50 microamperes? Okay, so let me write that over here. VGS is constant. Okay, VGS is constant, implies VGS is going to be 0.72 volts. Okay, the new ID is given to be 50 microamperes. Okay, the question is, what is the value of VDS? Okay, let me double check. What's the value of VDS? Okay, that's the question. How would you go about solving this problem?
We make an assumption.
Okay. What assumption are you going to make?
That it's in saturation, and then we check if it is correct or not.
Okay. Let's see. That's applicable in other similar problems, but here there is some more intuition that we can get. Okay. Let's park that to one side. We'll come back to that. So VGS from the previous problem is 0.72 volts. VDS was found to be 0.22 volts, and we were on the edge of saturation. Okay, what was the value of ID? ID was 100 microamperes. Okay, so we were barely in saturation. Okay, what happened?
Solve for VTH. We solve for VTH and the ID problem set equal to 50.
VTH is 0.5 volts.
Okay.
Okay, that's not going to change in this class. So you want to solve for VTH, you said? So VTH is going to take the value of VTH to be 0.5 volts.
Okay.
Okay, let's see what the problem is trying to do. The initial value of ID was 100 microamperes. The problem is trying to do what? reduce the current, right? Well, there are two ways to reduce the current. You can reduce the gate to source voltage, which he does not want to do. He wants to hold VGS constant, right? So let's say we try to increase the value of VDS. What happens to ID? And why do you think that happens? Let's just say, not in this case, okay, microamperes, okay. In this case, right on the edge of saturation, okay, on the edge of saturation, when I try to increase the value of VDS, what happens to ID? And why do you think that happens? Say that again.
I think the current is going to increase.
The current is going to, let's say, I'm going to erase this. One answer is that the current is going to increase. The other answer is going to be the same. And the third answer is going to be decrease. Okay, we have one person saying that the current is going to increase. Any other answers? So the question really is, we are at the edge of saturation here, and we have a drain current of 100 microamperes. What do you think happens when I increase the drain to source voltage? When I increase the VD, what happens?
Well, isn't VD equal to VGS minus VTH? If VGS is constant, then you have to change the VTH or nothing changes, right?
VDS equals to VGS minus VTH. When this equation is satisfied, we are on the edge of saturation. Okay, but when I increase this independently, then VDS is not going to be VGS minus VTH. So we are not in edge of saturation anymore. So we'll be in what region of operation?
Just regular saturation.
Regular saturation. In regular saturation, what do you think happens to ID if I increase VD? Remember the good old curve? There is the increasing ID, and then there is the saturation. This is VDS. This is ID. The very definition of saturation is what?
Constant current value.
Constant current value. By increasing VD, as long as I'm in saturation, the current should not change. Okay, so let me state that again. Okay, so it seems that as long as I'm in saturation, the current remains same. Okay, so I cannot, ID is not a function of VDS in saturation, right? Even if VDS changes left and right, the ID is going to remain constant. So the problem here is really asking us to reduce the drain current, not by changing VGS, but by changing VDS. So the problem is hinting to us that we should really be operating not in saturation region, but in linear region, this region. Okay, in this region, we were on the edge of saturation here. VDS is exactly equals to VGS minus V threshold. That's the edge of saturation right here. We are currently poised right here. And this is VDS. If we increase VDS, we will enter the saturation region and ID will become independent of VDS. On the other hand, if we go to the left of this equation, meaning that if we reduce the VDS, there is going to be a corresponding reduction. If we go to the left by reducing, ID is going to reduce because we are entering the linear region. Okay, so graphically, what the problem is expecting us to do matches what the behavior of the MOSFET. Okay, we are right now poised right at the edge of saturation, and in order to reduce the current, okay, what we have to do is to reduce the drain voltage. So I'm going to enter the linear region, okay, in linear region by reducing VDS. ID is reduced. Okay, is that really the case? I don't know. Let's look at the equation for current in the linear region. ID is mu n C oxide W over L VGS minus VTH into VDS minus 1/2 VDS squared. Okay, so there's as it turns out, this guy, all of this parabolic dependence, all of that decreases as we decrease VDS. Okay, so as a result, ID is going to decrease. Okay, now we have just about everything we need. Does that make sense at all? ID value, the new ID value that we want is 50 microamperes. The mu n value is known to be 450, or we don't have to do the math again. We calculated this to be K sub n, right? K sub n. All of this was calculated to be K sub n. And then you know VGS because you're not changing VGS. Okay, VTH value, you know that guy to be 0.5 volts. Okay, there is an unknown here. This guy is the unknown. Okay, that is the value that we want to find out. And it seems it's a quadratic equation. Okay, it's going to take the form of, if you rearrange this, if you plug in all the knowns, it's going to take the form of ax squared plus bx plus c equals to 0. It's a quadratic where x is VDS. Okay, and you can find the solution of this using minus b plus or minus square root of b squared minus 4ac by 2a will give you the solution to this. There will be two solutions to this quadratic equation. Make sense? Questions, please. Questions so far. So the key to solving B is really based on the fact by noting the drain currents. Okay, so notice the drain current. The drain current initially we started it out to be 100 microamperes in problem A. That was given. And we were operating in the edge of saturation region already. Okay, so if we enter the saturation region, VD becomes ineffective. It does not change ID. So it seems if you want to reduce the drain current, as the problem wants you to do, without changing VGS, if you look at the equation for this guy, let me clean this up. If you look at this equation for ID, it seems there are two knobs to change the value of the ID. If you want to change the ID, you could change VGS or you could change VDS in the linear region, right? But what he wants you to do, one of the constraints in the problem is that VGS should not be changed, okay? If you want to keep VGS a constant, the only knob to control or reduce the drain current from 100 microamperes to 50 microamperes would be to change VDS. You have to lower the VDS. Once you lower the VDS, you get a new lower value for the drain current. Make sense? Questions, please. Okay, so if you don't have questions, I'm going to have a question for you. Okay, I'll give you the two answers that you would expect for VDS here. VDS should have, the solution of this should have two, it should have two values, right? This is a quadratic expression. So it should give you two values for VDS, okay? VDS, let's look at the solutions that we get from these two values. Let's see, I don't know, VDS squared. One is going to be 0.06, the other is going to be 0.09, okay? Here, so there are two solutions to this, 0.06 volts, 0.39 was it?
Yes.
0.39 volts, okay. When you solve this quadratic equation, you get two roots. Which of these is correct? Or both of these, which of these is correct?
Value 0.06.
0.06 seems to be correct. You're right. And why is that the case?
Because if we choose 0.39, that's going to be in saturation.
That's going to be in saturation. So you got two values and you want to double check that VDS, compare that to VGS minus VTH. You know what the value of VGS minus VTH is? 0.22, right? 0.22. And if you plug in a value of 0.39 here, this is going to be greater than the VGS minus VTH. So it should operate in saturation region. But look what our assumption was. We wanted to operate in linear region, but 0.39 results in a saturation region. So it doesn't work for us. Okay, so the only solution is VDS is equals to 0.06 volts. Implies a linear region with ID is 50 microamperes. Make sense? Questions? Okay, so this is VDS, right? VDS. Okay, so I leave you to plug in all these numbers. You already calculated this to be K prime, K sub n. This value is VGS value, or as a matter of fact, you have this guy 0.22 already. That's the unknown. Okay, that is the unknown. Okay, so that's part B of the problem. Let's see if we can go further. Let's look at part C. Okay, let's look at part C. Questions so far, please. Okay, we have simply, and that's the reason why I spent as much time as I spent in the last class on these ideas of drain gate source, drain gate source. If the drain is, what is the edge of saturation? When is it in saturation? What happens in saturation? In saturation, constant current. Okay, constant current. Here the current is linear. Okay, at least so far. We are going to revisit this point. The current is not quite constant. We'll come back and talk about that later. Okay, but for now we assume it's going to be constant current. Okay, let's see. Let me clear all of this. Let me make it make all of this. Okay, so now let's tackle part C. Okay, To investigate the use of MOSFET as a linear amplifier, let it be operating in saturation region. Okay, part C says we are operating in saturation region, and VDS is given to be 0.3 volts. We can verify that VDS is greater than or equals to VGS minus V threshold. We calculated this value to be 0.22. So VDS is in fact greater than VGS minus VTH. So it is indeed in saturation. Okay, so what we want to do is find the change in ID resulting from VGS changing from 0.7 volts by plus 0.01 and negative 0.01. Okay, let's look at that problem. Okay, let's see if I can add another page here, and then we'll part C of the problem, add a page. Okay, part C of the problem is that we are operating in saturation region. VDS is given to be 0.3 volts, okay, and VGS is given to be 0.7 volts, okay. Is that correct? VDS is given to be 0.3, VGS is given to be 0.7 volts, okay. The problem is, so we should be able to calculate the ID from here. What's the value of ID? We should be able to calculate ID, okay, ID. Now the problem really asks, what is ID prime? What's the value of ID when VGS is 0.7 plus 0.01, or VGS becomes 0.71, okay? And what is ID prime? ID double dash, okay? What's the value of ID double dash when VGS changes from 0.7 by 0.01? Okay, so for VGS, for change in VGS, for VGS value increasing, VGS value decreasing, what would you expect the ID to be? Okay, let me first write out the equation for ID in saturation, because the problem says it is saturation, and we even verified that this guy is greater than VGS minus VTH. So I'm going to use 1/2 mu n C oxide W over L VGS minus VTH the whole squared. Okay, it seems we should be able to calculate the value of ID to begin with. Okay, even without doing the math, how do you think ID compares with ID prime? Okay, ID prime is this guy, right? Where the VG is higher than the nominal value given.
So ID prime is going to be a little more than ID.
Thank you. ID prime is going to be more than ID. Similarly, ID double dash versus ID.
It's going to be less than that.
Less than that. So I'm going to do ID double prime on this side. So it's going to be ID double prime is going to be less than. So because I increase the gate to source voltage here, when the gate to source voltage is increased, ID should be increased. So ID prime is higher, so on and so forth. You get the idea, right? So this is what we should expect. So let's see if we indeed get that. So let's first calculate ID is 1/2 mu n C oxide W over L. VGS minus VTH is 0.22 the whole squared. Plug in all the values. You should get some value for ID. Okay, what value you get for ID really is 86 microamperes. So you plug in, oops, sorry, My bad. Okay, 0.7. ID is given to be 0.7, right? So ID is going to be 0.7. VGS is 0.7 minus 0.5, the whole squared. So this is going to be 0.2, the whole squared. Okay, so it seems you get a value of 86 microamperes there when you plug in all the numbers. When you do ID prime, that is going to be 1/2 mu m C oxide W over L 0.71 minus 0.5, the whole squared, which is going to be 0.21, the whole squared. Okay, 0.21, the whole squared. And when you do that, it's going to come out to some number, definitely greater than 86 microamperes. So let's see, that comes out to be this guy. So you see that 0.21 squared, that comes out to be 94.8. And by the same logic, this guy is 0.19 squared, which comes out to be 77 point. So 94.8 and 77.6. 94.8 microamperes. And ID double dash is going to be 1/2 mu n C oxide W over L VGS minus VTH, the whole squared. So this is going to be 0.19 squared, 77.6 microamperes. I don't know and I don't care. Yeah, 77.6, 94.8. And that's in fact what we expected to see, right? ID prime is 94.8 microamperes. And that is in fact 86 microamperes. Similarly, ID double dash is 77.6 microamperes, and this guy is 86 microamperes. Okay, so the point is, in response to the increase or decrease in the VGS value, the ID goes up or goes down. Okay, the ID goes up or goes down. Okay, now we should be able to calculate the difference here. So all he wants to find the change in ID resulting from this change. Okay, so he goes on to find the change here. In one case, the change is an increase of 8.8 microamperes. So ID prime is higher by 8.8 microamperes. In the other case, there is a decrease by 8.4 microamperes. Okay, so by increasing the VGS value, ID is increasing. So change in VDS is 0.01, implies a change, okay, an increase in ID by 8.8 microamperes. Okay, VGS goes down by 0.01, implies delta ID goes down by approximately the same value. Okay, so this is the operation of linear behavior, right? For really small values of the inputs, okay? For really small values of the input changes, the output is going to change proportionally, not by square law, okay? If you think about it, this is the equation, right? You would have expected to see ID to change by a squared, right? But that did not happen. It seems there's a proportional increase. That is because the change in VGS is so small that the squared is almost proportional. Okay, that's the idea. Does that make sense? Questions, please. Okay, so the idea is we are operating like a linear amplifier. Okay, by changing VG linearly, ID changes linearly. For a small value for VGS, limit VGS tends to 0. For small values of VGS, okay, the output behaves like a linear amplifier. Questions? What questions do you have, please? Okay, so that's example 5.2. All we are doing is we are in a very conscious, mindful, smart manner. We are understanding if the MOSFET is in saturation or is it in linear region. Once we know that, the rest is all simple. If we are in saturation, we use the current for saturation. If we are in linear, we use the current equation for linear. And then it's all regular jugglery of numbers, massaging the equations and plugging in the numbers. Okay? So that's the idea of square law, ID-VDS curves. So we did not talk about channel length modulation yet. Maybe now is a good time to talk about channel length modulation. Okay. Questions so far, please. Okay. Let's revisit what we did in terms of ID-VDS curves. ID versus VDS curves. We know there are two equations. ID is mu n C oxide W over L VGS minus VTH into VDS minus 1/2 VDS squared. This is in linear region, and in saturation region, ID is 1/2 mu n C oxide W over L VGS minus VTH the whole square. Okay, if we were to plot this for NMOS transistor, so if I don't say anything, it's probably NMOS. Okay, if we are to plot ID versus VDS, we saw that there is a square law dependence in linear region, and then there is a constant current. So this guy is the saturation, and this guy is the linear. Okay, so there is the saturation region where the current, there is no VD term. See, there is no VD term in here, and that's the reason why it's constant. Okay, then there is the linear. Oops, then there is the linear term, whereas VDS increases. Okay, whereas VDS increases, ID increases as well. So this particular value, this particular point is the edge of saturation. We saw that, right? This is the edge of saturation. This is where VDS is exactly equals to VGS minus V threshold. Okay, towards the left of it is linear, towards the right of it is saturation, and right there, exactly at that point, is the edge of saturation. That's the edge of saturation. Okay, now what I want to do is to plot the relationship between these two. Dang it. Okay, there is ID, and on the x-axis I have VG. Okay, VGS. Okay, just like I was plotting VDS versus ID earlier, I want to understand how VGS compares to ID. Okay, the idea was that if you remember, if the voltage VGS is greater than or equals to the particular value threshold, okay, if this value is the threshold voltage, to the left of it, the MOSFET was on. To the right of it, the MOSFET was off. Remember, let me go back and show you that equation there, that relationship. VGS relationship. Let's see, where was that? Summary in the very beginning. Okay, right here. If VGS is less than or equals to V threshold, the MOSFET is on. If VGS is less than V threshold, the MOSFET is off. So if VGS is greater than or equals to V threshold, the MOSFET is on. If VGS is less than V threshold, the MOSFET is off. Okay, so let's see. Let me go back and try to plot how that appears. Okay, I'm going to go back here. Okay, so the argument is, as long as VGS is less than V threshold towards the left of this point, okay, there should be no current, okay, because the MOSFET is off. And once the voltage VGS increases beyond the threshold voltage, I should see a square law, okay, I should see a parabola. Square law dependence. Okay, that is how the ideal scenario would be. Okay, if you look at that, and that's how it's going to be. Okay, but in reality, something else is going to play out. Okay, a small modification is going to play out. Exactly at V threshold voltage, there's still going to be some current. Okay, that's going to be the idea, and then it's going to be zero. Okay, why do you think this is happening? We kind of talked about this earlier in one of the higher order effects, or something in between on and off. Okay, why do you think there is, at this point in time, exactly at VGS, towards the left of that, I should expect to see a zero current, but there is some non-zero current anyways. Why is that happening? Why is there a non-zero current towards the left of VGS? There is a specific phenomenon that we talked about in the last class. When VGS is approximately equals to V threshold, but it is still not quite equals to V threshold. It's less than V threshold, where the MOSFET is supposed to be off, but it's not off. What's that region of operation called? Okay, I'm talking about this area where the current really should have been zero. Okay, I should not expect to see any current. Okay, but because of a tap, like I mentioned, it's somewhere in between on and off. It's not quite off, it's not quite on. There is some leakage current. Remember, there is some leakage current. Let me go back. I'll show you what I mean. Okay, if you go back to the regions of operation of MOSFET, okay, all the way back, up, okay, right here, okay, I'm talking about this region that is in between off and that is in between on. See here, VGS is very close to VTH, but it's not quite there yet, in between, Okay, in between those two regions, it's between on and off, there is some leakage current. That's exactly what we are seeing here. That's exactly what we are seeing in here. Okay, the VGS value is very close to V threshold, which is this guy. Okay, that's the V threshold value. That's where it is, but it's not quite there yet. Okay, so there you would expect to see a zero curve, but it's still non-zero. Okay, this curve here represents the quadratic relationship. ID is proportional to VGS squared. Remember, in both of the equations above, go back to the equations. Okay, there is a squared dependence, and then there is a VGS minus VTH into VDS the whole square. Okay, when it is really small value, it is more or less linear region, and then there is a square law dependence. Okay, so that's the idea. The idea that both VGS, there's a square law dependence here in the saturation region. Okay, when VDS is greater. So this is more or less the idea of VGS versus ID curves. Okay, ID versus VGS curves. And in saturation, what happens is in saturation region, there's a square law dependence. Okay, there's a square law dependence. And this, by the way, this graph is the relation for this guy. ID is mu and C oxide. This is the plot of one in saturation region. This is where VDS is greater than VGS minus V threshold. Okay, that's the idea. Okay, so ID versus VGS. So VDS is greater than VGS minus VTH. There's a squared law dependence. ID increases proportional to the square of VGS minus VTH. So that's what we saw, right? ID increases as a square of VGS minus VTH. Okay, so then because of this, MOSFETs are referred to as square law devices. Okay, we can plot ID versus VGS, usually done or instead plot ID versus VOV. We can even plot ID versus VOV just by shifting the axis. Okay, here is the idea. Okay, the value for ID VGS curves. Okay, does it make sense? And if we were to plot ID VDS at different values, if we go back to this plot, ID versus VDS, and we plot different values, and if we plot for different values of VGS, okay, this is VGS2. We can even plot for a different value of VGS, okay. This is VGS3. This guy is VGS1. Okay, so the idea that there's going to be different currents in the saturation region and different VDSAT for different values of VGS. We can plot a family of curves. Okay, I'm not going to complicate this circuit here. I'll just mention that it is possible to plot a family of curves. Okay, there is this guy for one value of VGS, and there's another value of VGS that we can plot the drain current for, and for a higher value of VGS, and for a still higher value of VGS. Okay, so it's possible to plot a family of curves in terms of VDS versus ID. Okay, VDS versus ID has this form. Okay, VGS versus ID in saturation has this form. Okay, one has that form, VDS versus ID. The other has this form, VGS versus ID. Okay, so we are looking at, because there are two variables that change ID. We want to understand the dependence of IDS on both of those values. Okay, does that make sense? Okay, so I'm going to talk about, so this is all about linear saturation, regions of operation, so on and so forth. Okay, now I'm going to introduce a very interesting new topic to you, the idea of ID not being constant in saturation region. Okay, so far we assumed that ID in saturation region. So let me restate that. When I'm plotting VDS as a function of ID, in the argument I made was that in saturation region, the drain current is constant. Okay, in saturation region, the drain current is constant. Okay, that's an ideal assumption. That's rarely the case. Okay, it turns out that in saturation region, the drain current is not constant, but it has a slope, something like that. Okay, so the drain current that was supposed to be constant here. So if we were to look at just one plot, let me plot just one. Ignore the rest of these curves here, ignore all of these curves here. Okay, we are only interested in one plot. Okay, this guy. Okay, so far the assumption was that in the saturation region, the drain current is constant, independent of VD. But that's not the case. In real transistors, what happens is there is certainly some slope to it. There is some dependence of ID on VDS. Okay, so let me go back and modify for the channel length modulation. Okay, I'm going to modify for modify. We want to do this MOSFET in saturation region to include channel length modulation. Okay, so let's start by looking at the equation for ID in saturation region. Okay, ID is 1/2 mu n C oxide W over L VGS minus VTH, the whole square. Okay, this is the equation that we saw so far. Okay, and the argument that I kept making over and over and over again to the point of you getting frustrated was that ID is independent of VDS. There is no VDS term. Okay, there is no VDS term in the saturation region, and that's what gave us the clean straight line over here. This guy, the horizontal, really nice horizontal line that we got there was owing to the fact that even when VDS changes in the saturation region, ID does not change. Okay, that was the argument I kept making. That's farther from truth. Okay, the idea is that there is still going to be some dependence, and I'm going to show that dependence using a new term, 1 plus lambda VDS. Okay, so I'm going to enhance my model to get closer to real world behavior in saturation region. Okay, in reality, ID does have some dependence on VDS. Okay, as opposed to being completely independent of VDS as I assume. Okay, this lambda is called the channel length modulation parameter. Okay, so you can think about it. The relationship here appears more or less linear. Let's assume that all of this is really constant. Okay, all of this is constant. Everything inside the green highlight is constant. So as VDS goes up, ID has to go up because that's the equation, and it goes up in a linear fashion. As opposed to this guy, if VGS goes up, there's a square law dependence. So there is a quadratic dependence. But in terms of um, the VDS, okay, in terms of VDS, it really is a linear relationship. And therefore, if you were to plot VDS versus, so there is linear region, here is the assumed value, here is the assumed operation. But in reality, because of channel length modulation, there is going to be some dependence, okay, linear dependence. So if you were to plot the slope of this guy, ID, okay, if you were to extrapolate this guy, if you were to extrapolate that guy all the way to origin, it meets the origin at what is known as an early voltage, or 1 over lambda. Okay, we'll talk about that. We don't have to worry too much about it. All we have to think about is that this slope, change in ID for change in VDS. Earlier, I thought it was 0. Because the slope is 0, it's not changing. But now, as it turns out, because of what is known as a channel length modulation, it is not 0, but a very small value. It's supposed to be, the slope of this is supposed to be R naught is 1 over lambda ID. Okay, that's supposed to be the channel length modulation parameter. Okay, that's the idea of channel length modulation parameter, the slope of this guy. Okay, the inverse slope is defined as RDS. Sometimes I keep calling this as R naught. That is defined as 1 over lambda. Okay, 1 over lambda, which is the channel length modulation parameter. The only big idea that we have to understand here is that in saturation region, the drain current is not going to remain constant, but it's going to change as a function of VDS. Okay, and in order to show that, I'm going to incorporate a new term, lambda VDS term. Okay, so to incorporate the idea that the drain current changes as a function of VDS. Does that make sense? Okay, questions, please. Questions so far? Okay, so this is the enhanced ID-VDS curve, okay, in saturation region. So this applies to saturation region. Okay, so the new equations for ID that we are going to use here on out is ID is 1/2 mu n C oxide VGS minus VTH whole square into 1 plus lambda VDS, where lambda is called the channel length modulation parameter.
I have a question, Professor.
Yes.
So in here, we are considering the effect of change in VDS. But why do we call this as channel length modulation?
Thank you. Thank you. That's a perfect segue for me to move on to the underlying phenomenon that causes this. Okay, so in order to understand that, okay, here we are. I'm going to draw the idea of add a page. I'm going to draw the figure for a MOSFET. Okay, there is the source. Okay, duplicate that for a drain. Okay, I'm going to move all of this like so. And then there is a Okay, there is that guy, there is this guy. Okay, so here is the gate, that's the metal, and here is the oxide. Here is the source, gate, drain. Okay, now I'm trying to explain the idea of channel length modulation. Okay, channel length modulation. Okay, in order to understand the channel length modulation, and I'm going to explain it in really informal terms. Okay, just so we get a very good idea of it. The way the MOSFET operates, as you know, is when you apply positive voltage, okay, electrons are going to line up underneath the channel. Okay, so there's going to be underneath the gate. Okay, there's going to be, when there is enough positive voltage on the gate, meaning that when VG is greater than V threshold, okay, there's going to be correspondingly enough number of electrons to form a continuous channel between the source and drain, correct? Now, in order to make a current flow, in order to have a current flow, okay, in the drain, this is ID. In order for us to have this, we want to make sure that we apply a positive voltage on the drain. Remember, VDS should be greater than VGS. And in saturation region, VDS is large. VDS is greater than VGS minus V threshold. This is in saturation region. Okay, we don't have to be in saturation region for the drain current to flow. Okay, we can still set up some amount of drain current by having a positive voltage on the drain that is higher than the source. If this guy is negative in relationship to the drain, then electrons begin to flow from the source to the drain, and we can have a current in the opposite direction, correct? Now, let's see what happens if I keep increasing the drain voltage higher and higher. At some point, VDS is going to be much higher than VGS minus V threshold, or we are entering the saturation region. So what happens when I apply a really big positive voltage and when I enter saturation region is, earlier, let's pay careful attention. Earlier, I had a continuous channel, okay? A channel that is a perfect straight line here, okay? The profile was a perfect straight line. That's the channel. But because I'm increasing the number of positive voltage on the gate, on the drain, what happens is all the electrons here are going to be attracted into the drain, or in other words, the effect of drain is going to extend into the channel. Does that make sense? So because I have a large positive voltage here, the channel now is going to appear not like a straight line, but a tapered value, okay? So the channel here, it is still full of electrons, all right? There is enough number of electrons there, very good. But instead of being a straight line like this, a full channel like this, it has a profile because of the extremely high positive voltage on the drain. Does that make sense? So if I further increase the drain voltage, the channel is going to become shorter and shorter. Okay, it's going to be pinched off. That's what happens. Okay, there's this point, pinch off point. okay, that moves closer and farther away. This pinch off point is moving closer and farther away based on the positive voltage that I apply on the drain. If I apply a very little amount of positive voltage on the drain, then there is no pinch off. The channel is continuous. The channel is going to appear like this. Okay, the channel is going to be continuous between the drain, between the source and drain. Okay, but if I keep increasing the positive voltage here, okay, the channel, there's not going to be enough electrons towards the drain. All of the electrons that were supposed to be here are actually pulled into the, are pulled into the drain. There is enough positive voltage on the drain to attract all electrons away from here. So the electrons can only exist like so. Okay, if I further increase the positive voltage, okay, the effect of gate, the effect of drain is going to extend farther towards the source, and then it's going to keep pinching off. Okay, it's going to keep pinching off that channel closer and closer towards the source. Okay, so in other words, the drain extends its arm closer and closer towards the source as we have a higher and higher drain potential. Does that make sense? So in very crude terms, this is similar to having a drain that starts here. So think about what is happening. As I keep moving the drain voltage up and down, okay, when I move the drain voltage up, okay, when I increase the drain voltage, the pinch off is going to get closer. When I decrease the drain voltage, the channel is going to get closer to the drain. The pinch off is going to move farther. Okay, so as I keep increasing the drain voltage, the channel is going to become tapered, and it also begins to move closer towards the source. Okay, so this idea of moving the pinch off point closer and away from the source, that's called the channel length modulation. It's the pinch off that is happening as a function. So pinch off happens in saturation region where VDS is large. Pinch off happens as a function of VDS. Okay, that's called the idea of channel length modulation. And this pinch off point, if it's right there because of a very high positive voltage on the drain, let me apply this positive voltage on the terminal here. Okay, if I apply a really big positive voltage, there's going to happen, a pinch off is going to happen farther there, and it is as if the drain is extended all the way here in a very informal terms. Now, what is changing as a result of that? What parameter is changing as a result of that?
Channel length?
Channel length, thank you. If I go back earlier, I mentioned the distance between, let me go back to my slide here. I mentioned the distance between the drain and source. Okay, let's see, the distance between the drain and source to be channel length. Excuse me for that. I have to go, way far back into the, till I reach the region of operation right here. Okay, this guy. Okay, the distance between source and drain, I named it as L, right? The distance between the source and drain, remember? The physical separation between the drain and source, we call that as length. But what do you think happens when the drain extends closer to the source? The length is decreasing, the effective length is decreasing as a function of the drain source voltage. Okay, so please bear with me as I go all the way back down. Okay, here as a result of channel length modulation. the effective channel length, that is between the drain and source, and I'm going to show this using this color, that is the L effective, has decreased. So here is a very interesting leap that I'm going to make. Because of VDS increasing, pinch off point moves closer towards the source, so the L effective decreases. Okay, as the drain extends its reach further and further closer to the source, the effective length decreases in the saturation region. Okay, what do you think happens to ID? Okay, if you look at the expression for ID is 1/2 mu n C oxide W over L VGS minus VTH the whole square. Okay, earlier I thought the L was constant, but because of this pinch off moving closer to the source, okay, as VDS increases, the L effective, this guy, decreases. So as a result of an increase in VDS in saturation region, what happens to ID?
It goes up.
It goes up because L is in the denominator. So when VD goes up, L goes down. When L goes down, ID goes up. Okay. So as VDS increases, ID goes down. And in order to capture that um, dependence, I'm going to augment my ID equation in saturation to show that mu and C oxide W over L. I'm not going to mess with that L value. I'm just going to say VGS minus VTH the whole square into 1 plus lambda VDS. Okay, so it turns out that this relationship, that as VDS increases, ID increases, can be captured accurately using this enhanced channel length modulation parameter. Okay, this is called the channel length modulation parameter. Okay, so I have a tendency to repeat myself, and I know that it's for some people it may appear like a bit boring or too dragged on, but if you're listening to these concepts for the first time, I think it is important that I repeat myself and say it over and over again. But if at some point the overwhelming feeling of the class is that I'm spending a little too much of time, let me know. I can cut back and move on. Yes, go ahead.
How can we define the pinch off voltage?
The pinch off point.
Yeah, pinch off point.
So the pinch off really happens. It's hard to put it in an equation format. Okay, but if we look at the curves, we should be able to explain that. Okay, but for now, just bear with me that at the edge of saturation, the channel is between source and barely at the drain. That's the edge of saturation. But once you enter the saturation and keep increasing the drain voltage, the pinch off point is going to move closer and closer towards the source region. Okay, so and I'll talk about how the pinch off changes in just a second. Okay, but that's a good question. There is it's hard to, you have to look at the amount of charge, okay, that is present. The voltage difference between the drain and source and the gate in order to understand the pinch off. Okay, so let's see. Let me go back to the curve. That's exactly what is being shown here. There's a pinch off that is happening that reduces the effective channel length. The earlier I thought the channel length was supposed to be that guy, but because of channel length modulation, the effective length is decreasing, and that contributes to an increase in current. And that's the idea of channel length modulation. In saturation region, ID is mu and C oxide W over L VGS minus VTH times 1 plus lambda VDS. Okay, you can calculate this to be 1 over lambda n is an early voltage. So like I mentioned earlier, if we go back to the slides a bit, and extrapolate this slope. Okay, extrapolate this slope to the x-axis. They're all going to meet at what is known as an early voltage. Okay, the slope of that guy is the idea of channel length modulation. So 1 over this value will give you lambda. Okay, negative 1 over VA will give you lambda. Okay, so we don't have to worry too much about it. If I don't know if there are problems that give you VA, all you want to understand is that this slope is not 0. Okay, and that is happening because of channel length modulation. Okay, let's see. Let's take a quick look. That's the idea of channel length modulation. So unless otherwise specified, we are going to be using this new equation. Okay, we're going to be using this new equation in saturation region. So all of this is in saturation region. So let me saturate. So channel length modulation happens in saturation region. Okay,
Professor,
that's the
like,
idea of
what does the mu stands for?
mu n, right? Mobility of electrons.
Mobility.
Okay, mu n is the mobility of electrons. C oxide is oxide capacitance per unit area. Okay, for now we can assume them to be constant. W over L is the aspect ratio, width over L ratio. VTH is the width threshold. So good point. If I forgot to define mu n as the mobility, sorry about that.
And lambda is
Lambda is the channel length modulation parameter. Somewhere in
okay.
here, I must
Okay.
have mentioned that lambda is the channel length modulation parameter. Okay, channel length modulation parameter. Okay, good question. Other questions, please. So that's the idea of channel length modulation. So what we will do is in the next class, we'll come back to look at some more problems. Maybe we look at the body effect. So far, we have been conveniently ignoring the fourth terminal. Okay. So far, I kept drawing the drain. I kept talking about the source and the gate, but for way too long, we ignored the body. Okay, that's going to act as a back gate. Okay, body effect is also called the substrate effect or a back gate effect, so on and so forth. So we'll have to talk about how the body affects the operation of MOSFETs. We ignored this all along, right? So that's something we are going to talk about. Okay, and then a few higher order effects, and then talk about some problems. That's for tomorrow. Okay, so quick questions, comments, concerns. We talked about higher order effect called channel length modulation. Okay, from here on out, when I say the drain current, you want to use the equation that incorporates lambda VDS, 1 plus lambda VDS, unless I specifically ask you to take the value of lambda to be 0. So if you go back to some of the problems that are coming up, if you go a little further, some of them ask you to assume that lambda is 0. Okay, so unless you are specifically instructed to do so, you assume that the channel length modulation is present. Okay, so we'll come back to talking about the body effect and a few other higher order effects, and then move on from there. Okay, questions, please.
Can you show the channel length modulation? Yeah, right there. The equations. Okay? No, can you show the equations real quick for it? Down below.
This guy?
Yeah.
Okay. Other questions, please. All right, we'll stop here, and then I'll see you folks back tomorrow.